Right, dear students, we are meeting after a very long time. So this is the 7th lecture that I am delivering. The last lecture, I mean what we are discussing, what we are learning in this particular session is about Unit 2, Solutions of Higher Secondary Chemistry. Okay. So what we did in the last lecture, okay, when I checked, I found that the last lecture was telecast on 4th of June. Okay, so if you want to visit it again, it is the 4th of June, the date on which it was telecast. Okay, so what we did in the last lecture was on ideal and non-ideal solutions. Okay, now I told you that ideal solutions are those solutions which obey the Raoult's law under all types of conditions like concentrations, etc. Okay, and non-ideal solutions are those solutions which do not obey the Raoult's law. Okay, so obeying Raoult's law means that the graph of the partial pressure versus the mole fraction is a straight line. Okay, and not obeying the Raoult's law means that the graph is not a straight line, but it is in the form of a curve. Okay, so and non-ideal solutions means that the solution is deviating from the Raoult's law. There is a deviation from the Raoult's law. Alright. So deviation, there are two types of deviation. That was what we did at the end of the last lesson. There are two types of deviation. The first one is the positive deviation from the Raoult's law and the negative deviation from the Raoult's law. Okay, so I will again just remind you about the positive deviation from Raoult's law. Okay, positive deviation from Raoult's law. Okay, so this is the graph. We can explain this just with the help of a graph. This is a graph having two y-axis and one x-axis. Okay, this, the x-axis, it represents the mole fraction. Okay, so when there are two components A and B, so we will represent this axis as in the forward direction with the mole fraction of B. So mole fraction of B starts from 0 to 1, and that means the mole fraction of A will start from or 1 and end with 0. Okay, all right. And in this axis, the y-axis, we have the partial pressure of the gas on top of that liquid mixture. Okay, so the graph, what we learned in the last lesson was that if it is a ideal solution, then the graph will look like this. What is this graph? This graph represents partial pressure of B versus mole fraction of B. This is what the graph will represent. This is what the graph will look like if it obeys the Raoult's law. Okay, but since it does not obey the Raoult's law, the graph will look like this, a curve. Okay, now since the ideal, we can call this the ideal graph. Since the ideal graph lie above, since the actual graph lie above the ideal graph, okay, it is more than, okay, the partial pressures are more than that is expected. Okay, so we call it what? The positive deviation from Raoult's law. Okay, and similarly the graph of the BA component will be like this. If it is a ideal, that means this is PA versus XA if it is ideal, but since it is not ideal, it will be like this. Okay, all right, this is ideal, this is ideal condition, and this is PB versus XB non-ideal, or this is the actual graph. Okay, similarly this is the ideal graph and this is again PA versus XA, but it is actual or the non-ideal. And okay, if you combine these two graphs, then you get the total pressure. The total pressure, okay, we let's make it a dot here also. Okay, it is something like this. Okay, so this represents what? This line. Okay, the dotted lines, again the dotted lines represents total pressure P versus mole fraction. Which mole fraction? XB mole fraction. Okay, and this is again ideal condition. Okay, but since it is not ideal, the graph will be something like this. Okay, so this represents what? We can write it on the left hand side. So these two are together. Okay, so this represents what? This represents the total pressure versus XB. This is actual. Okay, so now you can see that the total pressure is more than the total or the actual pressure is more than what is expected under ideal condition. So that's why we call it what? We call it the positive deviation from Raoult's law. Okay, so this is your what we did in the last class. Again, I have repeated it once more. Okay, so there is no need to keep this for long, because this was already there. This is already there in the last telecast. Okay, so I'll just drop this portion only. I'll drop this portion, and on the right hand side of the blackboard, I will explain to you what the negative deviation looks like. Okay, so in negative deviation, again we can draw the axis. This x axis represents XB, and the y axis represents the pressure, the partial pressure of the components. Okay, let's call it small p. Okay, and let this be the expected or the ideal graph for similarly. Okay, it is PB versus XB. Okay, this is ideal condition. Okay, if the solution was ideal, this is the graph. Okay, but since the solution is not ideal, and since the partial pressure or the actual partial pressure will be less than the ideal pressure, it will be below, unlike here where the actual pressure is above. Here the actual pressure graph will be below. Okay, that's why we call it negative deviation. Okay, so this will be PB versus XB. This is the actual or the non-ideal mixture. This is non-ideal mixture. Okay, similarly, we'll make the graph for XA, or sorry, we make the graph for where do we write it? Okay, we can write it here only. We'll make the graph for PA versus XA. Okay, so straight line graph, this is for ideal. Okay, and since we are dealing with non-ideal, and since it is a negative deviation, the pressure will be less, the partial pressure will be less. So therefore, this will be what? This will be PA versus XA. This is the actual, or you can say non-ideal. Okay. All right. Okay, and the total pressure graph. Okay, for ideal condition. Okay, dotted lines again. This is, so where do we write it? Okay, let's write it here. Okay, we can write it here on the top. This is total pressure versus mole fraction. This is this is ideal, and this will be the actual. This will be the actual. Okay, instead of this, which is expected, the actual is this. Okay, so this will be what? Total pressure versus X, the mole fraction. This is actual, which means non-ideal. Okay, so this is how we explain negative deviation from Raoult's law. Okay, so now why do we call it negative? We call it negative because the actual pressure is less than what is expected in the Raoult's. So what is expected from an ideal solution. Okay, and example of this type of liquid mixture is chloroform plus acetone mixture. Okay, example of this, whether I told you in the last class or not, example of this positive deviation is ethanol plus water. Okay, so this is positive deviation, negative deviation from the Raoult's law. Okay, so see this carefully, and I will rub this board. Okay, now in the next explanation, what we are going to do is we're trying to explain why some solutions behave as ideal solutions and why some solutions behave as non-ideal solutions. Okay, and why some show positive deviation and why some show negative deviation. Okay, now for that, let's consider, supposing let's assume that we have a liquid mixture A and B. A and B are two mixtures, okay, two liquids, A and B. Okay, now consider liquid A. This is liquid A. Liquid A, all right. Now you know that liquid A, there are molecules of A everywhere in the bulk of the liquid, along with that on the surface. These are all molecules of A. So these are all molecules of A on the surface as well as in the bulk. Okay, so the molecules of A are in the bulk as well as on the surface. Okay, so therefore, how is the vapor produced? What happens during evaporation is molecules on the surface will escape above the surface, and thereby what is produced is vapors of A. All right. Now the question is this. The question is, now the molecules of A are bound by what is known as intermolecular forces. Okay, there is an intermolecular force between A and A. Okay, so what we have to remember is that when the intermolecular forces are more, then less molecules of A will be jumping above the surface, or less molecules of A will be escaping from the surface and then becoming vapors. Okay, so therefore we can write down more intermolecular force, then less will be the vapor pressure. Okay, why? Because if the intermolecular forces are more, okay, then the molecules of A it will be difficult for molecules of A to escape from the surface and then go into the empty space as vapor. So this is one thing you should remember. Or you can say less the intermolecular force, more will be the vapor pressure. Okay, if the intermolecular force between A molecules is less, then molecules of A can easily escape and go into the space as vapors. Okay. Now let's consider this. Okay. So suppose now we have got two liquids, A and B. Okay. When there is two liquids A and B, there will be A also, B also on the surface. See. So two liquids A and B. There will be molecules of A also and B also on the surface. As a result, even B will be forming vapors and A will also be forming vapors on above the surface like this. Okay. So molecules of both A and B will escape above the surface, and vapor pressure will be due to the partial pressure of A and partial pressure of B. Okay. Now three conditions will arise here. Okay. Number one, now intermolecular force between AA or A or BB same as AB. Then okay, so we'll understand this here like this. Okay, so therefore, when A and B are in a mixture, okay, so in this case there will be three types of interaction. A will be interacting with A, B will be interacting with B, and at the same time there will be a third type of interaction. A will be interacting with B also, or B will be interacting with A also. Okay, so under such situation, okay, if supposing the interaction of AA, if the AA interaction and the BB or the BB interaction is the same as the AB interaction, in that case, okay, there is no difference of there is no effect of this mixture on the vapor pressure of A or the vapor pressure of B. Okay, because whatever intermolecular force A experienced, before becoming this mixture, okay, is the same as after it came into the form of a mixture. Okay, so in such cases, this situation gives rise to what is known as a ideal solution. Okay, so number two situation is supposing intermolecular force of AB is more than that molecular force of AB is more. Okay, now see the situation. Okay, if the intermolecular force of A, okay, and B is more, if the intermolecular force of A and B is more than between A and A, okay, see the number of the vapor of A or the number of molecules of A that can escape into this space will depend upon what? Will depend upon the intermolecular force Okay. Now, if the intermolecular force of A and B is more, then obviously the amount of A will be less. In the same way, if the intermolecular force of between A and B is more than that between B and B, that means if AB is greater than AA or BB, if AB is greater than AA or BB, in that case naturally the amount of A that is on the surface will be less, the amount of B that will be on the surface, above the surface, will also be less. So that means the vapor pressure in this situation is less. So therefore, since it is less, intermolecular force of AB is more than that between A and B. Okay. So vapor pressure produced is less. Okay. This gives rise to negative deviation. This gives rise to negative deviation. Alright, so this gives rise to negative deviation. The third is intermolecular force of AB is less than AA or BB. Okay, again come to this particular figure diagram. Okay, so if now, okay, if the intermolecular force between A and B, okay, you see now on the because on the surface, see, we have got A, B, A, B, A, B. Okay, so therefore A is interacting with B. Now if the force of attraction between A and B is less, then naturally it will be easier for A to escape out. If it is easier for A to escape out, it means more molecules of A will be there on in the space. Therefore, the vapor pressure of A will be more. In the same way, if the AB interaction is less than BB interaction, okay, so if AB interaction is less than AA or BB, that means if the BB interaction is more than AB, if the BB interaction is more than AB, because see, B is surrounded by A only, so therefore more amount of B will be there on the surface. Okay, so more amount of B will be there on the surface, more amount of A will be there on the surface, above the surface, more amount of B will be above the surface. Therefore, what does it mean? The vapor pressure is more. So this gives rise to positive deviation. This gives rise to positive deviation from the Raoult's law. Okay, and I hope this explains why we have got positive deviation, negative deviation, why we have got ideal solutions. Okay, so the reason is all because of the intermolecular force of attraction. Okay, just so see this carefully. Okay, and then we'll rub this board. Okay, next now we are going to do a very important topic, in this chapter on solution. Okay, that topic is known as colligative properties. Colligative properties, and this is a topic on which almost every year you have got numericals to solve, okay, and various scoring also. Okay, so what is the meaning of this colligative properties? Okay, so we will first write the definition of colligative properties. So colligative properties are those properties of dilute solutions which depend only upon the number of moles of solute present and not on the nature of solute. Okay, so that is this is the meaning of colligative properties. Okay, it may not be clear to you right now because with this definition. Okay, but it will be clear to you when you see each of these colligative properties and then do problems on it. Okay, or listen to explanations on it. Okay, so colligative properties once more. Okay, colligative properties are those properties of dilute solution. First of all, colligative properties are properties which are shown by dilute solutions. Okay, why do we call it dilute solutions? Dilute solutions because only dilute solutions behave like ideal solutions. Okay, so one of the essential requirement for colligative properties is that the solutions must be ideal. Okay, that means it must obey the Raoult's law. Okay, and you have seen that in the ideal solutions, all the solutions may not be ideal. All right, all the solutions may not be ideal. It may not obey Raoult's law. But if you make the solutions very dilute, that is one of the conditions for ideal behavior. If a solution is made very dilute, okay, then that dilute solutions will obey the Raoult's law. Okay, so therefore, colligative properties are shown by dilute solutions. Means that colligative properties will be shown only if the solution is ideal. Okay, so colligative properties are those properties of dilute solutions which depend only on the number of mole of the solute present. Okay, and not on the nature of the solute. Okay, so it depends only on the number of mole of the solute. Okay, not on the nature. So consider supposing you have got two solutions. Supposing say 5 m sugar and 5 m say glucose. All right, two solutions, 5 molar sugar solution. Okay, let's write down solution and 5 molar glucose solution. Okay, there are two solutions. Okay, 5 molar, this is your 5 molar sugar solution and this is your 5 molar glucose solution. Okay, all right. Now both are different, isn't it? Why they are different? Because this contains sugar and this contains glucose. Glucose and sugar are different. They are two different compounds. Their nature is different. Their nature is different. Okay, but they have got the same number of moles. What is that? 5 moles per liter. Here also it is 5 moles per liter. So therefore, since they have the same number of moles, they will have the same number of molecules, isn't it? Because why? Because 1 mole contains 6.023 into 10 to the power of 23. Okay, so this contains 5 into 6.023 into 10 to the power of 23 molecules of sugar. This contains again 5 into 6.023 into 10 to the power of 23 molecules of sugar. All right. So say both contains both are different compounds. Both are different compounds, different chemical reactions, different properties, etc. Okay, but the number of molecule is, the number of mole is same, and when the number of mole is same, it means the number of molecules or the number of particles are also same. Okay, so according to this colligative property, they have the same number of molecule. So therefore, the measurement of colligative property will be same in both these two different solutions. Okay, so that is the meaning. Okay, so first of all, we will just write down the list of colligative properties. So this is the list of colligative properties which you have to study in this chapter. Now, number 1 is relative lowering of vapor pressure. Number 2 is elevation. Okay, so write down these are the colligative property. Okay, colligative properties. elevation of boiling point. 3. Depression of freezing point, and number 4 is osmotic pressure. Okay, so how many? There are 4 colligative properties which we have to do one by one. Okay, the first one is relative lowering of vapor pressure. The second one is the elevation of boiling point. The third one is the depression of freezing point, and the last is the osmotic pressure. Okay, and while studying each and every colligative property, first you have to develop an expression. You have to develop an expression for this colligative property, and secondly, you have to prove that this is a colligative property. You have to prove that this particular property is a colligative property. What it means is that you have to prove that this property, or the relative lowering of vapor pressure, is not dependent on the nature of the solute, but it is dependent only on the number of mole of the solute present. Similarly, you have to prove that the elevation of boiling point is a colligative property. Okay, you have to prove that the elevation of boiling point does not depend upon the nature of the solute, but it depends only on the number of moles of the solute present. Okay. So today we will manage to do just start the first colligative property, which is relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay. First of all, focus your attention to this lowering. Okay, lowering of vapor pressure. Okay. So therefore, what it means is that, see, supposing you have a solvent, water. Consider you have got solvent, water. All right. So again, you have got molecules of water. Okay. These are the molecules of water. These are molecules of water. Okay. So therefore, these molecules of water will be escaping out, and as a result, you get, what do you get? You get vapors of molecules of vapors of water. All right. Okay. Now, supposing you have got this is pure solvent. Okay, this is pure solvent, this is water. Okay. Now, supposing you have got a solution. Now, you have, say, this is a solution. Consider, supposing this is sugar solution. Okay, sugar solution. Okay. Now, again here now, but when you have a sugar solution, okay, the surface is not totally filled with water, isn't it? Because now you have got water molecule and, say, sugar molecule, water molecule, sugar molecule, water molecule, sugar molecule, etc. Like it will be like this, isn't it? Okay. So the smaller one is your water, and the larger is your sugar molecule. Okay. So, okay, it is logical that since the total surface area is not filled by water molecule, you will get, there will be less amount of vapor. Okay. So therefore, this is what? Vapor. All right. So from these two, you can say that when a non-volatile solute is dissolved in a solvent, the vapor pressure of solution is lowered. Okay, so this is the reason. When it is pure water, the vapor pressure was more. Okay, why it was more, I explained this. Okay, because the surface is entirely filled with water molecules. Okay, so when you dissolve sugar, all right, you can, this is a sugar. Okay, let this be a sugar. When we have got sugar, then see the entire surface area does not contain water molecule. So therefore, there will be less amount of water molecule on the surface. So the vapor pressure is less. So therefore, we say that when a non-volatile, okay, we are using the term non-volatile. Okay, here see I would like to mention one thing, that in the in the solutions that you studied prior to this colligative properties, you studied about liquid mixtures. A and B. A is also liquid, B is also liquid. Liquids are supposed to be volatile. That means liquids are supposed to give vapors on top of their surface. Okay. But here we are talking about non-volatile. Okay. So when we are discussing sugar solution, it is not liquid plus liquid. It is solid plus liquid. Okay. Sugar plus water. Okay, so when we dissolve sugar in water, this is a mixture, but it is not a mixture of solid liquid plus liquid. Okay, when we mix liquid plus liquid, both are volatile. But when we mix solid plus liquid, the solid is generally not volatile. Okay, except few solids like say iodine. Okay, the solid is not volatile. So when the solid is not volatile, listen to this carefully. When the solute is not volatile, what it means? It means the vapor pressure will be only due to the solvent molecules. Only solvent molecules will be there on the vapor. Only solvent molecules will be present in the vapors, because sugar is not volatile. Sugar will not be present on the vapors. Okay. Alright, so this is what you have to understand. So when a non-volatile solute, okay, non-volatile solutes, sugar, salt, urea, glucose, all non-volatile solute. When it is dissolved in a solvent, then the vapor pressure of solution is lowered. Okay, that's why lowering of vapor pressure. Okay, only so whenever a solvent makes a dilute solution, or whenever a solvent is converted to solution, then the vapor pressure of the solvent will always be more than the vapor pressure of the solution, or the vapor pressure of the solution is always less than the vapor pressure of the solvent. So we call it lowering. Okay, now we will explain what is relative lowering. All right, so for this let non-volatile solute A be dissolved. Okay, let's call it B. Okay, let non-volatile solute B dissolved in solvent A. Okay, so this is the picture. Okay, this solvent is your A. Okay, now we have got the solute, which is your B. Okay, so we will have solvent molecules as vapors on the surface Okay, now let XA XB be mole fraction of A and B in solution, mind you. Okay, obviously it will be solution only, because A and B is present in solution. A and B, they are not present in the vapor, mind you here. So solution. Okay, and let PA be the partial vapor pressure of A. Okay, now again here also notice carefully that we are not assuming the vapor pressure of B. Why? Because B is non-volatile. We don't have any vapor pressure of B. Okay, and we are saying let PA be the vapor pressure of A. We are not saying the partial vapor pressure of A. Okay, I told you partial pressure is a term used only when there is a mixture of gas. Here there is no mixture of gas. there is only gas, there is only vapor A. So therefore we simply call it vapor pressure of A. Alright. So now according to Raoult's law, what do we have? We have partial pressure, sorry, again, the vapor pressure of A is proportional to the mole fraction of A. Alright. Or PA is equal to K into XA. Alright. This is question 1. Okay. Now, let XA is equal to 1. Or you can say when XA is equal to 1, PA is equal to PA naught. Vapor pressure of pure liquid A. Okay, so here you understand. So this we have already studied Raoult's law. That what is that Raoult's law? The vapor pressure of a liquid component is directly proportional to the mole fraction. Okay, so this is the mole fraction. This is the mole fraction of the solvent XA, and PA is the vapor pressure of A in solution. Okay, when it is in the form of a solution. Okay, so when you solve this proportionality, you insert a constant K. Okay, so to find the value of constant K, there is a technique in science. What is that technique? You impose some conditions. What is that condition? You say, supposing let XA is equal to 1. Now, when XA is 1, okay, I told you I think that this before, because you know that XA plus XB is 1. You have studied this, that the sum of the mole fraction is always equal to 1. When the sum of mole fraction is 1 and XA equal to 1 means XB is 0, right? Okay, when X equal to 1 means XB is 0. So XB is 0 means there is no solute. There is no solute. There is no solute means the liquid is pure liquid. Okay, or the solvent is in the pure form. So therefore, when XA is equal to 1, we can say that the vapor pressure is equal to the vapor pressure of pure liquid or the pure solvent. Okay, so we say that PA naught is the vapor pressure of the pure liquid or the pure solvent. Okay, so therefore, substituting in 1, we get, what do we get? We get PA is equal to XA into, dot, okay, XA into PA naught. Okay, so this is the expression we get. This is the expression we get so far. Okay, now this is there is no need to number right now actually. Okay, we can number it. This is number 2. All right. Okay. Now since XA plus XB is equal to 1, therefore XA is equal to 1 minus XB. Okay, so you can replace XA by 1 minus XB. What do you get? Therefore, you get PA is equal to 1 minus XB into PA naught. Alright, okay. So we will just continue here. Okay, I am just putting an arrow here. We don't need this now. So we'll continue it here. So that this is what we have got so far. PA or the partial pressure of A, not the partial pressure, sorry, PA or the vapor pressure of A is equal to 1 minus XB. 1 minus XB is the mole fraction of solute into PA naught. Okay, if you simplify this, you get PA or is equal to PA naught minus PA naught into XB, or PA naught minus PA is equal to PA naught into XB. Alright, now see there, what is this? This represents what? This represents lowering of vapor pressure. Why does it represent lowering of vapor pressure? Because PA naught is the vapor pressure of pure liquid and PA is the vapor pressure of solution. We have already shown that the vapor pressure of solution is always less than that of solvent. Alright, so therefore this PA naught minus PA represents the lowering of vapor pressure. Okay, so or we can write down PA naught minus PA upon PA naught is equal to XB. Okay, see this expression. Okay, this expression, what does it show? Now this is lowering of vapor pressure. This is the total vapor pressure. This is lowering of vapor pressure, and this is the total vapor pressure of, or you can say this is the vapor pressure of pure solvent. Okay, so therefore this whole expression is known as relative. That's why the term relative. Okay, lowering divided by total. So therefore this is, so therefore we can write down, therefore relative lowering of vapor pressure is equal to mole fraction of solute. Alright, so therefore from this expression you can say that the relative lowering of vapor pressure is equal to the mole fraction of solute, XB. Alright, so before I rub this, let me do some explanation, okay, on this. I told you before that there are two things that we generally we generally discuss and then try to understand while learning about colligative property. Number one, we try to get a mathematical expression by which we can solve problem. Okay, that you will learn later on. Okay, at the end of this particular topic. Okay, so therefore this is the expression that we were talking about. What is the expression? If you know the vapor pressure of the pure solvent, you know the vapor pressure of the solution, then you can, the expression is vapor pressure of pure solvent minus solution divided by the vapor pressure of pure solvent is equal to the mole fraction of the solute. This is the expression I was talking about. Using this expression, you can simplify this expression and use it for problems. Okay, that is number one. Next, I told you that in this particular topic, you have to prove that this is a colligative property. Now, how do you prove that it is a colligative property? First of all, to prove that relative lowering of vapor pressure is a colligative property, you have to do this derivation. After deriving, at the end you get this expression. After you get this expression, you will find that the relative lowering of vapor pressure is equal to the mole fraction of the solute. Okay, see, so this is the mole fraction of solute. So this mole fraction of the solute, it means the relative lowering of vapor pressure is dependent only on the number of mole of the solute present. Does not depend upon the nature of the solute. Okay, the relative lowering of vapor pressure, once again, the relative lowering of vapor pressure is equal to the mole fraction, which means this colligative property depends only on the number of moles of the solute and not on the nature of the solute. That's why it is a colligative property. Okay, all right. So this is regarding the relative lowering of vapor pressure. Now, what is left in this relative lowering of vapor pressure is we have to simplify this expression further and then try to work out some problems on this particular expression. Okay, this we will be doing it in the next class. Okay.